Hi everybody, Miss Maritello here. In this video, I'm going to talk about vertical stretches and vertical compressions, as well as horizontal stretches and horizontal compressions. Taking a look at our very first problem, it's a vertical stretch. So you might be noticing on here, we got the red graph is like our original, and then the blue graph is going to be our transform graph. So hopefully you're noticing here, it seems kind of like the red graph, it got like stretched upward, pulled upward. So that's what we call a vertical stretch. We're stretching it upward or pulling it upward there. Just like picture sometimes like a rubber band getting pulled up. So taking a look at some more specifics on here, the red or orange graph is f of x, and then the blue one here is g of x. So if I give you guys the equations, again, the f of x graph, it's just f of x equals x squared, and then we're seeing for the other one, we got g of x equals 5x squared. So you're noticing we got 5 times the x squared. So like our change in the equations is we're multiplying the x squared by 5 now. So if you're looking at your function values, it's like we're doing 5 times the f of x value. So remember f of x is like your y value. So then if we're doing, it's 5 essentially times the y value. So that's affecting the y values in the y-axis. So that's why this is considered to be a vertical stretch. I also usually think about it like it's being stretched upward. And then if you take a look at those y values, I know some of them you're not able to see on here because it's a smaller graph, but like specifically though, you could look at like say the point -1, 1, that gets moved to be -1, 5. Or like the point 1, 1 gets moved up to be 1, 5. And then even like if you took a look at say -2, 4, you can't see it, but then on the blue graph, that would be all the way up there. Then at 220, -2, 4 would move up to 220, or like +2, 4 moves up to +220. So it gets really steep up there because all the y values are getting multiplied by 5. We call that a scale factor of 5. Let's take a look at a compression. So again, we got f of x here. It's the red one. It's the original graph, f of x equals x squared. And then the blue one, I'm hoping you're noticing it kind of looks like the blue graph is like pushed down. It's like if I took the red graph and I just kind of pushed it downward. So that's a compression when we're like pushing on it. And so we're pushing it downward. If you look at the equations here, you might notice the g of x then it's equal to 1/4 times x squared. So you're going to notice instead of having like a whole number, a number greater than 1, now we have a number less than 1. And that's causing us to like have the graph be pushed downward. So if you look at the function values, that's like 1/4 times whatever f of x was equal to. And then if you look specifically then like at your y values, you're going to notice that all the y values are 1/4 of what they were on the original. So like 16 times 1/4 is 4. 4 times 1/4 is 1. Sometimes people prefer to think about it as like dividing by 4. 16 divided by 4 is 4. 4 divided by 4 is 1. And if you go specific, like looking at the graph, so if I was to look on the red graph, say at 2, 4, or I'm sorry, -2, 4 right here, it goes then to -2, 1. So again, that y value is being divided by 4. And again, we're pushing it downward. So still vertical, but now we're going more downward. And we have that like k value that we would refer to now as a fraction. We got 1/4 there, and that also is our scale factor. So just kind of summarizing with these, whenever you have a vertical stretch or compression, you're going to see a numerical value multiplied by the function value. So I put on here f of x is equal to k times g of x. If the k is a number bigger than 1, then we're going to be stretching the graph upward. So that's kind of like that first example I showed you guys, we're stretching the graph upward, and the scale factor is just whatever the k is. On the other hand, if you have a k value that's like in between 0 and 1, then it's like the graph is being pushed downward. We call that a vertical compression. So that's where we're like pushing, I'll call it pushing downward. And again, that's when the k value is in between 0 and 1, like a proper fraction, 1/3, 1/2. That'll cause the graph to be compressed. And again, it's like that k value is multiplied by the function value. So it's like the k value is getting multiplied by the y value. So that's why the y value is affected. Let's take a look now at our horizontal stretches and compressions. obviously we know horizontal has more to do with like left and right and with, of course, the x values. So here we got our very first horizontal stretch graph. So I still have on here, the red graph is like the original, and then the blue is like the transform graph. And again, horizontal stretch, I like to think about that like we're still stretching, but now we're stretching horizontally. It's kind of similar actually to the vertical compression, and you might notice that as we're going through. But so now I'm stretching outward. So because I'm thinking about it as horizontal, I'm stretching outward. So for this one, again, we got f of x equal to x squared. And then for this example, I have the blue one listed as p of x, and I have p of x equal to 1/2 x squared. Please notice that the 1/2, it's in parentheses with the x. Remember, that's what changes the x value. It causes the transformation to be considered to be horizontal. So if you were to go through and say like simplify that equation, notice like to do 1/2 x all squared, it would end up being 1/4 x squared. So that's why there's some like relationship between the horizontal stretch than with the vertical compression. But for our purposes, we're looking at it, we got the 1/2 x in parentheses, all squared, so this is a horizontal stretch. And again, you're looking at it, that 1/2 is right in there in the parentheses with the x, so we're affecting the x value. Now, taking a look at this again, I noticed like I'm stretching outward. That's always how I think about the horizontal stretches. What's interesting though is if you take a look at the x and the y values, you're noticing the y values are all the same. That makes sense because again, it's a horizontal stretch, so it should be the x values that are changing. However, when you look at those x values though, you're going to notice that the x values are actually multiplying by 2. So even though the equation is p of x equal to that product of 1/2 x raised to the second power, our scale factor is actually 2. Even though the equation has in there the 1/2, the scale factor actually comes out to be 2 because look at all those x values. So like for example, if I look at my original, say my ordered pair -2, 4, when that gets stretched outward, that specific point then moves to -4, 4. Or if I was to say, look at the ordered pair -1, 1, when I stretch that outward, it goes to -2, 1. When I can do the same thing like on the other side of the parabola as well. 1, 1 becomes 2, 1, and then 2, 4 becomes 4, 4. So again, it's like those x values, they're actually getting multiplied by 2. So you could say that the scale factor for a horizontal stretch, it's actually the reciprocal of whatever the k value in the equation is. Kind of interesting. All right, and then let's take a look. Oh, and again, I kind of circled it on there for you guys. So notice again, the scale factor, it's 2, even though our k value is 1/2. And then taking a peek next, then I wanted to give you guys an example of a horizontal compression. So here you're going to notice f of x graph again, it's the red one, f of x equals x squared. And then the blue one, it's like we kind of pushed the graph in. We're pushing in the red graph. So that's a compression then because we're pushing inward. So if we take a look at some specifics on this one, we got the tables there, we got our equation. So again, the original is f of x equals x squared. And then I called the blue one here q of x. And the q of x is equal to that product of 2x raised to the second power. So notice please again that the 2, that's like our k value, it's in the parentheses with the x value. So that's how we know then that this is a horizontal transformation. Because again, that k value, it's right in the parentheses with the x value. So when we take a look at this, some of the specifics with the ordered pairs, as you look at some of these ordered pairs, so say like I look at the -2, 4. When I look at how that changed when we get to the blue graph, the -2, 4 is actually becoming that -1, 4 when we're like pushing it inward. And then say I look at -1, 1, that actually goes to -1/2, 1. Or if I'm going on the other side, this point that was at, say, 1, 1, it goes to 1/2, 1. Or the point that was at 2, 4, it goes then to 1, 4. So you're actually noticing here that the x values are all 1/2 of what they originally were. So even though here our k value is 2, the scale factor is actually considered to be 1/2 because look at those x values, they're all half of what they originally were. So kind of like what we noticed before, for these horizontal stretches and compressions, the scale factor is actually half of what the, or I'm sorry, the scale factor is actually the reciprocal of what the K value is, which is interesting. And again, I always remember with the horizontal compressions, that's where then I'm pushing inward. So I always remember as we kind of like start to summarize this, when I'm thinking about a horizontal stretch, it's like I'm pulling outward. And again, horizontal side to side. So it's like I'm pulling outward. And then the compression is like you're pushing inward. So specifically then for horizontal stretch or compression, that K value, it's inside of the parentheses with the X. That's how we know we're affecting the X values. That's why it's a horizontal transformation. And again, if the K value is in between 0 and 1, like you got a proper fraction, then that would be a horizontal stretch. It's kind of like we're stretching outward. Now remember though, when you go to find your scale factor, it's really the reciprocal of what the K value is. And then on the other hand, if you're going to be having a horizontal compression, then your K value is going to be bigger than 1. So like it could be 2, 3, 4, 5, even a different, could be a fraction as long as it's bigger than 1. And so again, you're going to notice that K value, it's inside the parentheses with the X. And then when you go to think of the scale factor, it's going to be the reciprocal of whatever the K was. And then just as a little reminder too, so remember like the vertical stretches, that's where you're either stretching upward, and that would be the K value is greater than 1, or a vertical compression is when we're pushing downward. That's where your K value is going to be less than 1, more like a proper fraction. And then when we do a horizontal stretch, kind of like pulling the graph outward, for a horizontal stretch, you're going to have a K value in between 0 and 1. But then if you're going to be pushing inward for horizontal compression, that's where the K value is greater than 1. I hope this video was helpful. Thanks for watching.